We're going to be talking about section 4 today. We're going to talk about zeros of polynomial functions. Some of this is not new. All right. We said that a polynomial function of degree n can have at most n real zeros. Let's think about that for a minute. It definitely has n zeros, but not all of those have to be real. So it doesn't have n real zeros, it has at most n real zeros, okay? So if the degree is 5, it could have 5 real zeros or 3 or 1 or whatever. Of those real zeros, they could either be rational or irrational. So for example, what's a rational? So it could be like plus or minus 5, right? 7, negative 2, and so on. 1 over 7. Irrational. Good, yeah. Okay, and so on. Okay, so this, just another example here. Okay, so here's a rational zero theorem. Okay, the rational zero theorem gives us a way to come up with a list of possible rational zeros. Because, take a look. Suppose you have a polynomial with degree 5. I know that this polynomial can have up to 5 real zeros. And perhaps some of those are rational numbers. So here's one thing I could do. If I have no way, here's one thing I could do. How many numbers are there in the universe? How many rational numbers in the universe? Right. So what I could do is I could sit down and try every single one of the infinitely many rational numbers. But that's just not a good way of doing things. If you're ever stranded on a beach, right? Okay. Now, there is a way. The rational zero theorem gives us a way to narrow down that list from the infinitely many numbers to like 6 or 8 or 12 possibilities. Okay? You've seen this before. So basically, if you have your polynomial, then this first coefficient and the last constant are used to find a list of possible real zeros. So what it is P, right, is something that we give a name to. You know this, P and Q. P is the factors of the constant term. Q is the factors of the leading coefficient. So, hang on. Then what we do is we take P over Q. Okay? I know you've seen this before, so let's just do one. For P, I look at the constant. For Q, I look at the coefficient of the leading term. Obviously, it's the easiest case when Q is the factors of 1, right? So, P are the factors of 4. So, the factors of 4 are 1, 2, and 4, but also negative 1, negative 2, and 4, correct? So, I say plus or minus 1, 2, and 4. A little bit of shorthand. The book might have different notation. Okay? I like my notation. All right? This is more efficient. And then Q is going to be just plus or minus 1. So then P over Q is going to be every single P over every single Q. So in this case, it's going to be plus or minus 1, 2, 4. So if you look at this corollary, if the leading coefficient is 1, then P over Q is just the factors of the constant, right? It's just the P's. You don't even have to do that step. This is it. What we have now is a list of all possible rational zeros of f of x. How many numbers are on this list? 6. So what does this mean? How many total zeros is this function allowed to have? 3, right? Because it's x cubed. So we're allowed to have 3 zeros. Suppose, some of those were real, okay? And suppose of those real zeros, some of them were rational. So basically, if this function has a rational zero, it has to be either 1, 2, 4, -1, -2, -4. Okay? So -3 can't be a 0. -2/3 can't be a 0. Does this give you any information on irrational zeros? Can √3 be a 0 of this? Possibly. Possibly, we don't know. Only the rational ones, right? We only have information on the rational ones. Okay. One way to narrow down the search further is to use Descartes' rule of signs. So this is telling you, Descartes' rule of signs is my favorite, and we're going to do it, and we're all going to be experts at it today. Basically, we now narrowed it down from infinity to 6. Descartes' rule of signs tells you this function can only have 2 negative zeros. That means you could throw away one of the negatives. Do you see what I mean? Like, it narrows down even further. Okay, so let's do it. Basically, for Descartes' rule of signs, what you want to do is this. The number of positive real zeros, okay, possible, is equal to the variations in sign of f of x. The number of negative real zeros is the variations of sign of f of negative x. Again, I find that with this, it's easier if I just do one for you. Okay? Let's just do one. Okay, so we have f of x. We want to jump from one coefficient to another and see how many times the signs will change, will vary. So take a look here. What's the coefficient of the first one? +1, right? So positive, then it switches to negative. So there is one change there. And then it's negative. Here it changes to positive. So there are 2 times where the sign changes from positive to negative and vice versa. So I say the number of positive zeros is 2. Or, now here's Descartes' rule. Whatever number you extract from here, you have to, from that number, keep subtracting 2's. Why 2's? We really don't care. Okay? You keep subtracting 2's until you can no longer subtract a 2. So, if this is a 2, it's 2 or 0. Suppose this was a 4. Then it would be 4 or 2 or 0. Suppose this was a 5. Then it would be what? 5 or 3 or 1. And that's it. Suppose that was a 1. Then it's just a 1. Okay. Now, for the number of negative ones, we want f of negative x. That means what we're going to do is we're going to make all of the x's negative. You know the shortcut? I'm only going to write it in this much detail one time, then we're never going to do it anymore. So do you see what I did? Now, what's this going to be, the first term? X to the 4. What about the second one, positive or negative? Negative, negative, positive, right? 3x cubed. What about the next one? Negative 5x squared. So look at what happens, guys. Negative x to the power of 3 is negative. Negative, negative is positive. Negative x squared is positive times negative is negative. Here, negative, and then plus 7. So look at what happened. Comparing f of x to f of negative x. All the ones with even exponents kept their sign. Do you see that? All the ones with odd exponents switched their sign. Okay? The constant will keep the sign. So the next one we'll do it with that shortcut. Okay, so here, how many times do the signs switch? 1, 2. 2. Okay.
Sorry. I thought you were talking about B.
Okay.
My bad. I thought you were talking about B.
So the number of negative ones is 2 or 0. So now we make a chart. Positive, negative, imaginary. And then what you have to do is this. You have 2 or 0 for the positive, 2 or 0 for the negative. What you have to do is you have to match each one of the purple ones with each one of the blue ones. All right, and take all of the possibilities. Yeah, so we match this one. So we have 2. Okay, here's how I do it. Imagine this is team A and this is team B, and this is a competition. Each person in team A has to face off with each person in team B. So 2 with 2, 2 with 0. And then 0 with 2, 0 with 0. Okay? Huh? Was it here? So it's positive and negative. We have this, and then we have this. We sort of like compare them when we want to match each one like this, and we arrange them into our pluses and minuses. This is Descartes' rule. Okay? And now we need to complete the last column. The condition is, whatever the degree is, each row has to add up to the degree. What's the degree of this function? What's the degree? 4. So each row has to add up to 4. Does the first row add up to 4? Yeah, I have nothing to add, so 0. The second one adds to 2. What should I add to make it 4? 2. Last one ends, same thing. And what about the last one? 4. Okay? Now, this column is in possible imaginary solutions. Imaginary solutions always come in pairs. You can either have 2, 4, 6, 8 imaginary numbers or 0. Never 1, never 3, never 5. So this column must always be even. All right? Now let's do another one. Let's do this next one. Yeah.
So I understand how you got the solutions, but what do you do that with the 0, 2, 2, and 4? I think it's just multiple numbers for the different solutions.
So you got how many did these two?
What?
Did you get how I did these two?
Yeah, I just
Okay.
how you did the chart. I'm just confused what you do with the now, what you do with those solutions from the imaginary solutions. It's just like multiple zero solutions.
You're confused about how I got these numbers?
Yeah, I understand you thought them. I'm just not. I guess I'm just not sure
what it means.
Yeah, I guess.
What it means is this problem, this function has 4 zeros. Okay? And this tells you the possibilities. So, this Descartes' rule is telling you that you can have 2 positive or 2 negative solutions for this. Or, right? So, by looking at this, can I have 3 positive solutions? No. Can I have 4 negative solutions? No. Right? That's what it tells you. The numbers in this column are always going to be even. Because it's the number of imaginary solutions. Imaginary solutions always come in pairs. Okay, let's do this one. So for the number of positive ones, how many times does the sign vary? 1, 2, 3. So it's 3 or 1. The number of negative ones, we want f of negative x. So what you do is this. The ones with the even exponents, you copy them as they are. The odd exponents change sign. Even stays, odd changes, constant stays. Okay? So there is one sign change. So the number of negative is just 1. So now I have 3, 1 with 1. So positive, negative, imaginary.
We have to do something about it.
Okay, 3, 1, 1, 1, right? Yeah, and these are the only possibilities. Here? No, because you only got 1 negative. Why did that erase? So you match that with that and that with that. So now, what goes in that column? 0 and 2. Okay? So this has 4 solutions possible, right? This has 4 zeros. Can the zeros be negative 2 and negative 3? No, because you're only allowed 1 negative 0. Okay? Okay. Why do we use this? Later on, you know how you do P over Q and then you have to try out every single one? Well, now, if you know that it has 1 negative, you don't have to try negative 2 and negative 3 and negative 4 and negative, you know what I mean? If with the negatives, you're done with them, you're done with them. Okay. Complex zeros. I'll tell you. Complex numbers are numbers that are real and imaginary combined, right? So we know this already. A polynomial function of degree n has at least 1 0 in the complex number system. So basically it's saying if you have a polynomial function where the highest exponent is greater than 0, it's got to have a solution. That's it. Can you think of a polynomial function that doesn't cross the x-axis? I can't. Right? So that's what it's saying. Mm-hmm.
Oh, the parent function one?
Right, or that doesn't have an imaginary solution. Right? There is it. It's the fundamental theorem of algebra. Okay? So every single polynomial has at least one solution. Okay, so linear factorization theorem. We know this too. If a polynomial has a degree of n, how many zeros does it have? N, which means it has n linear factors. Okay? Because from each zero, n zeros means n factors. Because from each zero you can get a factor. Okay. A function has complex zeros when its factored form has a quadratic factor with no real solutions. So suppose you have a function and you factor it and you get x plus 7, x plus 3, and then x squared plus 2, right? What's the degree of this function? 4. Right? Because you multiply all these. Degree is 4. How many solutions is it supposed to have? 4. How many real solutions does this have? 2. This gives you an imaginary solution. Right? So, where did we get this imaginary solution from? Because we have a quadratic factor, right? So it has 3 factors here. This one's quadratic. Can it be factored? No. So we call this an irreducible quadratic factor. Okay? And that will lead to imaginary numbers. So for example, a function might look like this, right? It might be degree 4, but crosses the x-axis twice. Okay? All right, so let's do this next one. Okay? We're going to solve this. Here we go, putting it all together. It says, write K as the product of linear and irreducible quadratic factors. So let's do that. All right. We're going to do P over Q. There is a coefficient of 1, so it's just going to be the P, right? So P over Q, we're just going to look at the 24. We ignore the sign because it's going to be plus or minus anyway.
I get that.
So it's plus or minus. What are the factors of 24?
1, 2, 3, 8.
4, 6, 8. I like going in order just because. Yeah. Yeah. Okay. All right. So now, what you got to do is this. You have to try every single one until you find one that gives you a remainder of 0. Remember that? Okay. You could do this in a couple different ways. You could go in order, plus 1, minus 1, plus 2, minus 2. You could do it like Vegas style and just pick random ones and see if you get lucky that way, right? That's what I want to do today. I'm going to start with minus 2. All right, I'm going to start with minus 2. So here, we put in, I'm going to tell you guys, yeah. 1, but it's not going to be any quicker than this. 1, 1, negative 13. Okay, so this comes down, negative 2. All right. I'm giving my throat a break. Score. It worked. First try. I totally hadn't tried this before at all.
Companies out.
1, 2, 3, 4, 5, 6, 8, all 16 of them.
It's my favorite thing ever. Still works. I know it works. It works. Here's negative. Okay, so
14 is negative.
I have
You're supposed to negative 23 plus 22 and 1 is negative.
oh, I messed up my negatives.
And then the 4 now.
But it still works, I promise. Now we're good. Now we're good. So I have x plus 2, and then the depressed polynomial, x to the 4 minus x cubed minus 11x squared minus x minus 12 equal to 0. Oh my gosh. What about now? You do it again. So now, couple of things. You can do P over Q for that red one again. Whatever zeros the red one has, are those going to be included in the original list that we did in purple up there?
Yeah.
Of course they are. However, this is a 12, so like the 24 and stuff like those won't work, right? So let's just do a randomly different one. I thought did you say 4? I heard somebody say 4. Let's do 4.
Yeah, I thought I heard someone say 4 also.
Yeah.
So on a test, would it just be a random numbers?
I will tell you what to do on the test. I have a very
Organized.
So 1, 4. I give you a head start on the test. Well, now I need to factor this. There's no way to factor this, so I need to do synthetic division.
So what do you do with
X plus 2 we're going to keep for later.
Oh.
So now I get 12, 1, 4, 3, 12, 0. So I have x plus 2 from before. Now from the red I got x minus 4, x cubed plus 3x squared plus x plus 3 equal to 0. Now, when I get to my cubic function and I have 4 terms, my first instinct is to try to factor by grouping. If you can factor by grouping, do it that way. Otherwise, you have to do the synthetic divisions again. The thing is, you can factor this by grouping. So, I have x plus 2, x minus 4. Now here, I split this down the middle. So from the left, I can factor out an x, and I get x plus 3, plus 1 times x plus 3. Okay, equals 0. So x plus 2, x minus 4. Here I'm going to factor out the x plus 3, and I have x squared plus 1. So, what was this telling me to do? Write as a product of linear, we're not solving just yet. Write as a product of linear and irreducible quadratic factors. And we have just done that. X plus 2. Huh? It's plus. So you can, if it was x minus 1, you could. Okay, let's see what we have here. We have factors. Linear factor, linear factor, linear factor. This is a quadratic factor, and it can't be factored the way we know it. So it's an irreducible quadratic factor. So this is it. We're done with part A. Now this says, no, That's not good enough. You've got to do it in terms of linear factors. So it's telling me, I don't want any of this. I can't factor this polynomial stuff. Go and factor that. Okay? So here's what we do. So what we have is x squared plus 1, right? If only we had x squared minus 1, we could have factored it, right? If only. So, check out what I'm going to do. Nothing is impossible once you get to pre-calc, okay? I have x squared plus 1. Does minus minus make plus? Yeah. So what if I write this as x squared minus minus 1? Oh my god, now I can, oh my god. Now it has a minus. How would I factor this? X squared minus 1. Right, because you take the square root and the square root, correct? And you put plus or minus. So here, I'm going to take the square root, plus minus, and now, what's the square root of negative 1? I. So I put I and I. I know. Right? So now,
Guys, the secret is to know what is the secret password.
so now I can rewrite this as a product of linear factors. Isn't that cool?
Is this good? Yes. Is it going to screw me over during the test? Yes.
And now it says, okay, now that you factor this thing, list all the zeros of k. Okay, x equals negative 2, positive 4, negative 3, plus or minus I. Huh?
Yeah.
Of course. So now, how did I... This is the graph of that function. Listen. On the homework, I don't want you to sit there and try every single one until you get one with a remainder of 0. That's an inefficient waste of time. I want you to graph it. So you graph this and you look, oh my gosh, there is a 0 at negative 2. Let me start with negative 2. So we start with negative 2. That's how I did it. Okay? So we start with negative 2. Then I need to do it again, right? Okay, what should I try now? What else is a 0 here? Oh, the 4. Okay, let me do 4. Could I have done negative 3? Sure, I just didn't. I did one negative, one positive. Now, all this work is there. I'm not eliminating any of the work. All this work is there, right? I'm just making it more efficient. Okay, now somebody's going to ask me what if it's on the non-calculator section. Then I'll just tell you, assume that x equals 2 is a 0. And then you just go with that. Okay? I've done this before. I got this. Okay? So, what I want is for you to be able to come up with negative 2, negative 4, negative 3, plus or minus I. Okay? And then, so that's how you can do the homework. Now, let's do one more here. Write a polynomial function of least degree with real coefficients in standard form that has cube root of 5 as a 0.
Wow.
Yeah. So if 2 is a 0, then I know the factor is x minus 2. right? Okay, so how do we get cube root of 5 as a 0? There must have been an x cubed, right? So, because the index is 3, okay, I say x to the power of 3 minus 5 equals f of x. Is that right? Does that, if I were to solve this, does that give me the right 0? Yeah. So, suppose then, the 0 wasn't cube root of 5. Suppose the 0 was 4th root of 5. What would you do then? X to the 4th minus 5. Suppose it was, negative 5th root of 2. Right. Okay? Yes? Yes. Okay. So, tomorrow, you will have the quiz. Tomorrow's Friday. Yes. You will have your quiz.